Inclined plane video 1. This whole series is about considering inclined planes without friction. So the aim of this video is to consider the forces and components of those forces acting on a block that is placed on a smooth inclined plane. At the end, this is not essential to follow, we're going to look at the motivation for breaking forces down into components and the directions in which we choose to break them down. So we'll start with the example question. A block of mass 5 kilograms is placed onto a smooth slope inclined to an angle of 30 degrees. Before even doing the question, looking at the parts A, B and C, we need to draw this out to make sense of it. So it's inclined to 30 degrees, meaning that. And then we've got a block sitting on here. It's got a mass of 5 kilograms. We should consider the forces that act on this. So we've got the reaction force. If something sits on a surface, there must be a reaction force. And then we have the weight, which in this case will be 5g. Part A, calculate the components of weight parallel and perpendicular to the slope. So we'll deal with these parts one at a time. To do this, we need to redraw the picture. Here's the center of mass of the block, and weight acts down on that block and has a size of 5g. Then we can add in the components of weight. So one of them, like that, must be perpendicular to the surface. The surface is that. Perpendicular to the slope. There's also a component of weight that's parallel to the slope. Parallel to the slope. Just to make that completely clear, if we pick up that component, you can see it lies in the same line as the slope itself. See how the dashed green arrow is aligned with the slope. The angle of 30 degrees, the angle of inclination of the slope, can also be found inside this triangle as well. You can show that if you do the following. This angle here must be 90 degrees. That must be 60 degrees, so that the three angles in that triangle add up to 90. Then this angle must be 90 degrees, and so whatever's left here must be 90 minus 60. When working quickly with these, it's important just to know that the angle of inclination is always the angle that goes in here, the one that's been highlighted. Okay. So let's look at the perpendicular component. To do that, we need to name the sides here. This side is the adjacent in the triangle we're looking at, and this is the opposite in the triangle we're looking at. And we're looking at that triangle there, made up of 5g, an adjacent, and an opposite. So for the perpendicular component, we've got adjacent and hypotenuse. The 5g is the hypotenuse. So if we're dealing with adjacent and hypotenuse, we should use cos. So cos of 30 degrees is equal to the adjacent, which we don't know, divided by 5g, the hypotenuse. If we rearrange that, 5g cos 30 degrees is equal to the adjacent, the perpendicular component. So that's one of the answers to part A. We do the same for the opposite component, the component that's parallel to the slope. So parallel to the slope. Here we're dealing with opposite and hypotenuse, so we should use sine. 5g sine 30 degrees is equal to opposite, so that is OP, P, over 5g. 5g sine 30 degrees is the opposite, which is the parallel component. So we've got the two answers to part A. And if we refer back to the question, it states calculate the acceleration of the block. So we'll redraw this 30 degrees. Before we determine acceleration, we should have apply some common sense. And as this object has no friction acting on it because it's on a smooth surface, it's got to accelerate down the slope if it does. And we apply the reaction force. To determine acceleration, we need to consider Newton's second law. Use Newton's second law. And we apply Newton's second law along a specific direction. We'll work down the slope. We're doing that to follow the acceleration. It's usually just a bit easier to do that. So the only force here that acts down the slope is this, the 5g sine 30. So it's only a component that acts down the slope. We can consider the other forces, or the other components. This 5g cos 30 is perpendicular to it, so it has nothing to do with down the slope. And then r also is perpendicular to the slope, so it has nothing to do with motion along the slope, or the parallel component. As 5g sine 30 is the only component acting along the slope, it is the resultant force along the slope. So by Newton's second law, we just call the resultant force ma. Then we can start to work this out. We'll let g equal 9.8. So we've got 49 times 1/2. 5 times 9.8, 49. Sine 30 is 1/2. The mass of the block is 5. And the acceleration is what we'd like to know. So 24.5 divided by 5 equals acceleration. 4.9 is the acceleration, so 4.9 meters per second squared. Okay, let's look back at part C. Calculate the reaction force. So the reaction force acts entirely perpendicular to the slope, so we should apply Newton's second law perpendicular to the slope. You can see previously we applied it parallel to the slope, now we're moving on to look at perpendicular to the slope. R is acting in that direction, up, out, and perpendicular to the slope, so that's R. And then for weight, we can see that the yellow highlighted 5g cos 30 degrees acts into the slope. That's the opposite direction. That's opposite to what we're looking at here. As it's opposite, we must make that negative. 5g cos 30 degrees, and that's equal to ma. But we know here that a must be 0, because it doesn't accelerate into the plane, into the slope, or out of it. It does neither of these things. It doesn't sink into it like that, nor does it rise up off the surface. So it's not accelerating perpendicular to the plane. So we're allowed to say a is 0. So then we can write r minus 5g cos 30 is root 3 over 2 is equal to 0. Now if we move 5g root 3 over 2 to the other side, we've got r, so that's 49 over 2 multiplied by root 3. The reaction force is 42.43 newtons. Okay, referring back to the optional point, just under the aim. So we're going to look at the motivation for breaking forces down into components and the directions in which we choose to break them down. Why use components? At GCSE you will have seen simple uses of Newton's second law. Let's say we have a block of mass 2 kilograms and there are a few forces acting on it, a 30 Newton force, a 12 Newton force, and then acting the other way, a 18 Newton force. We know if we apply Newton's second law to this and we take right to be positive, 30 plus 12 minus 18 must be equal to ma. They come together to make ma the resultant force. 24 equals 2a, therefore we get an acceleration of 12 meters per second squared. That's simple, and that's easy to use. We can use the forces because they're all lined up with each other. If we were to take those forces, it's possible to show the 30 Newton force, the 12 Newton force, and the 18 Newton force are all parallel. But as soon as we change one of these, so let's take much the same situation, a 2 kilogram object sitting on a surface, same forces are applied, 12 newtons to the right, 18 newtons to the left. We'll apply 30 newtons, but you see we're applying it at some angle now. Intuitively we know that's not going to be as effective at sliding this along. Or if you want to pull something towards you, you pull it straight towards you. You don't pull it at some angle, sort of up over your head or down towards your feet. You're not going to be as effective. The same with this 30 Newton force. It's now not going to be as effective as it was in the first situation. So we look at components so we can consider how much of that force actually contributes to the horizontal motion. That's the question we're trying to answer. So how much of the 30 Newton force contributes to horizontal force? And this is why we use components. If we break the 30 Newton force down, and we'll say that the angle was theta in there, this dash component just drawn here, we might as well call that how much the 30 Newton force pulls right. And we can use trig to work this out. We're interested in the adjacent down there. The force itself is always the hypotenuse. We know we've got a right angle there because we deal with a horizontal and a vertical component under these circumstances. And if we're dealing with adjacent and hypotenuse, we're using cos. So cos theta equals the adjacent over 30, adjacent over hypotenuse. 30 cos theta is equal to the adjacent. We can now see the effect of the 30 Newton force horizontally. If we look a little further at the cos graph, but just the first portion, that's cos theta against theta from 0 to 90 degrees. You can see as the angle theta increases here, this is what the graph shows, as theta increases, cos theta decreases. So 30 cos theta also decreases with theta. Once we've broken things down into components, we can see what actually interacts with what. We could redraw that picture with the 2 kilogram block, with 18 newtons pulling left, 12 newtons pulling right, and then a component of 30 cos theta pulling to the right. If we apply Newton's second law, we'll take right to be positive again. We'd have 30 cos theta pulling right, plus 12 pulling right, minus 18, minus as it's pulling left, equals ma. If we knew theta, we would then be able to work out the acceleration. Okay, that's the motivation behind considering components.